for my desktop. So, okay. Thanks for joining this meeting. Welcome, everyone. I'm going to talk about BurnTx today, a security issue in Lisk and all its forks. I'm going to talk to you in a small group such that we can all work together to fix this issue before it becomes a major problem and people start abusing it. My name is Simon Vata. I am active in the Lisk community as Prolina. A little bit about my background and my motivation for doing this. I'm just a random guy from the internet, which means I have no connection to Lisk or Lisk headquarter at all. I co-founded Kulo, a secure communication solution, which gave me a kind of knowledge about security and usability. I'm a board member of the Prolina Foundation, which makes the name Prolina from the Prolina delegate. I'm interested in proof-of-work alternatives, which is why I got into Lisk. I'm not an investor. I bought a stack of Lisk for €100 in spring just to play around with it. So my motivation is purely technical, and yeah, I'm not interested in price at all. I contribute to Lisk on GitHub as Webmaster 128, and I'm active in the Lisk community as Prolina delegate. Yeah. So I'm going to get rid of my video now because you see me here, I'm there, and show you what's going on. First of all, I download a fresh copy of Lisk Nano. I'll check it from here. What do we need? This for my Mac. Download. We are using Lisk Nano because there's a user interface bug in Lisk Hub, which is very annoying for the purpose of this demonstration. So other than that, there's no particular reason I'm using Nano. But if we used Hub, we needed to close and reopen Hub every single time I send a transaction. So we replace the thing, and we confirm that I got the right version of Nano there. So this is the hash, just to confirm there's nothing manipulated in the client, which is the exact same hash sum we're expecting here. Okay, let's go Nano. Okay, here you see this is the Nano I just downloaded from the internet. And what you see here is I use a custom node. This is a node that is connected to the internet, to testnet. I'm using a private host name here, but this is just for shortcut purposes. You can't connect to this host because it's local only, but it's just a regular testnet node. I'm using this throwaway passphrase here that you can see. I mean, it's this one. It's nothing special. Just prepared that one. Okay, as you can see, we are connected to my own node. and this node is manipulated in a way that that we can do harmful things. So the first thing I want to show you is we send transaction to, let's look at the agenda, to the address 24, and we send like 3 Lisk. Okay, we get the confirmation. We send 3 Lisk to number 24, address 24 on testnet. What happens now? Okay, the transaction is processed. We see it here. Okay, this is what we submitted. Let's wait until we get the block. Oh, here we go. This is our transaction. We sent to the address 24, but the address, the recipient address changed to something with 44 to whatever, very long. But let's see what happened on the real testnet, testnet explorer. Here we go, the transaction. Oh, we already have it here. This is our transaction we just sent to 24L, and it goes to some different address. We can check 24L if the money is there, and we see nothing. It's not there. We can do that with a different address, just to confirm we did nothing wrong here. We go to 23 now and send another 3 Lisk to 23 here, yeah. This is locally signed by the original nano and sent to my manipulated node. And in the meantime, we can check the opposite direction. Did this address get the money on testnet? We just sent there, and there we see it's 3 Lisk. We just sent at 10:06. It's at a wrong address. The second example we have here goes to the one we sent to 23 goes to this address. So someone else. Oh yeah, someone else got our 3 Lisk, which is a pity, because we wanted to send it to 23. Now I ask you to send me a random address from Lisk testnet, just anything you want me to send money to. It won't harm the address, so just throw something into one of the chats and we'll use that. Otherwise, I can generate random addresses, no problem. If you're all too shy, it's no problem. By the way, this is the manipulated node that we are running, so nothing crazy here. Okay, nobody's volunteering. All right, then I generate a random address in front of your eyes. I'm using Python 3 to generate a random address within the range 0 to the biggest possible value. Okay, here we go. We have a random address. Oh, there we got an address from the audience, so we prefer this one. Where's now? We sent to one address from the audience. This one gets like 12 Lisk. Yeah, this is the confirmation that we sent to 14377 and so on. We're waiting for the block, 12 Lisk to this address. And here we go, we get another manipulation. The address changed from 14377 to 014377. And when we check the recipient will see, okay, our transaction never occurred here. So let's have a look at the other address. Yeah, here we go. There's our money. So the money goes to a different account, which is a pity. So we have seen two different kinds of manipulations, one from very short addresses to something kind of random, and a manipulation that appends a leading zero to the address. So why is this? We have in Lisk and related projects, we have an address space that goes from 0 to the largest 64-bit integer, and we use Python because it has proper integer types to get the biggest unsigned 64-bit integer value. And here we go, this is it. So this is the largest possible address. Now, this is, I think, 21 characters. Let's check this in the editor. Yeah, this is 21 characters. But the largest value that is allowed by Lisk is like 22 characters and all nines. So we go with 5 and 20 and 9. So let's confirm the length. Yeah, it's 22 characters long. So this is what Lisk core considers the largest possible address, but actually we can only generate addresses in the 64-bit range, which goes up to this number. So everything above that number and everything additionally, everything with leading zeros, something like 0, 1, 2, 3, is a valid address as well, but is not in the unsigned 64-bit integer range. Now we are going to look into the code, how this can happen actually. And for this, I prepared an installation where we got a checkout of the Lisk repository as well as a checkout of the Rise repository, and see where this this problem occurs. We go to Lisk. What we have here is a checkout of the latest head of the 110 branch, and just to confirm, the latest the latest commit we have here is the current testnet version. What I prepared is to install all the dependencies, but other than that, as you can see in the status, no manipulation here. So let's check how the Lisk code behaves when dealing with numbers for the recipient. We have this big num helper. We use it from the local helpers directory, and now we convert a recipient address, the largest possible value, to a buffer, which is what we do when serializing the transaction before it is signed, as well as before it goes into the block payload. What we have here, okay, we have an 8-byte buffer, which represents this address. When we have a smaller address, we get a smaller but still 8-byte value, which is great. What happens now when I exceed the 64-bit range by changing this 5 into a 6 is something strange. We don't get 8 bytes anymore, but we get 16 bytes. This is, let's call it a feature of this toBuffer function. I don't know if that is intended behavior, but that happens when your value exceeds the 8-byte or 64-bit range. What we here have now is 16 bytes. And what Lisk core does now is it cuts the first 8 bytes and uses that as an address, which means this address has the same byte representation as the address 1. See, we cut the first 8 bytes here, which is the same as this one, which means we have 2 different recipient addresses that lead to the same binary representation, and that allows us to change the recipient address without invalidating the signature. So second example is I go with the address 123, which is relatively small value, 7B at the end here, but always 8 bytes, great. And now I can put as many zeros as I want, and it still becomes 7B. See, I can generate how many different addresses as I want. They all map to the same byte representation, which is obviously a problem. We have the same code in Rise, which inherits it from Lisk. We installed all the dependencies just to check where we are. Status. Okay, I modified the package log because I installed dependencies. Other than that, we are on development and currently at this commit from Saturday. So copy. Since Rise uses TypeScript, we run TS node instead of node to reproduce the error. Import the big num helper in the TypeScript fashion, and then we see the same behavior. The numbers that can be represented as 8 bytes are represented perfectly fine. If we exceed that range, we get the 16 bytes again, which are cut. Then the same behavior for trailing zeros. I have 1, 2, 3, and I can add some leading zeros, leading zeros. We have the same byte representation. Okay. For rise, this is used. See somewhere in the code here. Here we go. This is where we use this big num helper to generate a serialization of the recipient from the recipient from JSON, and we use that to feed it into a byte buffer during in the get bytes method. And in Lisk, we have this helper here, big num. Here we go. This is where we use the big num helper to get 8 bytes from the recipient address. Okay, this is it. Okay, obviously we don't want to have this kind of addresses which can never be derived from a public key. But we also don't want to have them as recipient addresses. We don't want to have recipient addresses with leading zeros, and we don't want to have recipient addresses that exceed this this largest possible value. So this is why I prepared a patch for Lisk that can be applied similarly to Fox. I will make this patch available to you. It's currently private, so you have all the time and to review it. What we have here is a list of exceptions, which is recipient addresses that are already in the Lisk blockchain that have trailing zeros, leading zeros, sorry. Here we have the transaction ID and the address that this is mapping to. I don't think there is any kind of manipulation like I showed you going on here. The list of addresses that are not plausible, so they are not coming from a pub key, is so small that you can safely assume that this is just from people playing around and hacking some whatever address into the recipient field. Here we have the list of addresses exceeding the 64-bit integer range. The same for testnet. The one above was from mainnet. So coming to the fix now. uint 64 max is the largest possible 64-bit value. It's exactly the same that we have here, that we calculated from Python before. Here we have throw in some custom exceptions for testing purposes, and what we do here now is actually the fix for that. Here we have just some renaming. In this block, we check if there's an exception with for an address with a leading 0. And if there is an exception, we make sure that the recipient ID stays this fixed recipient that we added in the exception, and no one changes the recipient ID to something without leading zeros or something with more leading zeros, because all of them lead to the same signature. And we want to have this really strict fixed behavior here. And here is where the real fix is for the leading 0 case. We assert that the recipient string, which is basically the address, but we cut the DL at the end, must match the number representation of that address when converted back to string. So this is normalizing the recipient address. We convert it to an integer, a big num, and convert it back to string, which cuts all of the leading zeros. And if those don't match, meaning if we have leading zeros here, we throw an exception. This is the second case, exceeding the 64-bit integer range. If we have an exception, we make sure that the recipient address remains the one that we fixed in the exception. Otherwise, we do the regular test, where we test that the recipient number, which we got from JSON here, converted to a big num, this recipient number must not be greater than the max value of unsigned int. Yeah, and as soon as we get a recipient address that either exceeds the 64-bit integer range or is not normalized, this transaction becomes invalid. So the function we are talking about here is, here we go. That's the getBytes function. GetBytes is a strange name for serialize. So this is where we convert the JSON representation of the transaction into bytes that we can then sign, or we can use those bytes to create the payload for the block, for the payload hash. Here I added a comment to ensure we preserve this legacy behavior, because this code does not make exactly clear that when the recipient number exceeds the uint 64-bit range converted to a buffer of size 8, this is 16 bytes. But we need this behavior to persist in order to be able to validate the transactions that are in the blockchain already. And here it's just a renaming. There's a couple of tests for that. I test that we get all the exceptions. I test that, I test that we get all the exceptions for leading zeros. I test that we don't get into trouble when we send to 0L, which has, of course, a leading 0, but is perfectly valid. And I test legacy transactions, that behavior, and also test that you cannot change the recipient address that we fixed in our exceptions list above here. So I make sure that you cannot replace this address with an address that has less than 1, 2, 3, 4, 6 leading zeros. Okay, I will make this patch available to you in private today. I have it in a private repository. You can review it, you can test it, you can ask me any questions about it. I successfully synced a testnet and a mainnet node from zero with this patch applied. Speaking about this patch, we have one node here, that's testnet 03, which is the one we used in Lisk Nano to send our transactions that get manipulated. And we have another testnet node here, which is testnet 04, where this patch is applied. And what we see here is that this node where the patch is applied does not accept the block generated by the transaction we sent to testnet 03. See, this is the block. We check if that has something to do with us. Testnet block, okay, there's a transaction. And yeah, this is one of the transactions we sent. Actually, the first one we wanted to send to 24L, but it went to an address that is exceeding the 64-bit integer range. That is our transaction. And the patch node does not accept this transaction anymore. It does not accept this block. We get the exception that I wrote here, invalid payload hash, because recipient address number exceeds unsigned 64-bit integer range. So I'm pretty sure this patch does the job, which is good. Okay, time to discuss the possible attacks on that. The first thing is we can manipulate nodes where clients directly connect to. This is what we saw just now. I did that with my own node where I whitelisted my IP address only, so nobody else is getting trouble with this kind of attack. I connect to my node and make this node responsible for sending my transaction to the network. This node cheats on me, manipulates my transaction, and then sends it to the network. This is the first attack that we have on the transaction. Second attack is obviously in the transaction pool. We manipulate yeah, which basically means that we need to spawn a couple of nodes, and those nodes take transactions from the transactions pool, manipulate them, and broadcast them to the network again. The amount of nodes we need for this depends on how reliable the attack needs to be. I mean, we just need to make sure that the manipulated transaction is reaching the fogging delegate. So if we want to have a very high success rate for our manipulated transaction to reach the fogging delegate before the original transaction reaches the fogging delegate, we need to spawn a good number of nodes, maybe 200, 300, 400 nodes in the network. And then we tweak the attack a little bit and make sure our nodes send to more than the normal number of peers. So our transaction is spreaded faster. We can also reset the relay count to make our manipulated transaction even more popular. If we just want to cause irritation and destruction by burning money while sending it to a different address here and there, and just want to make some random chaos, we don't need that many nodes. So I estimate we can just spawn 1,000 nodes and manipulate a transaction here and there, which will already destroy the trust in Lisk pretty much, and it gets even harder to debug this issue. The next point where we can manipulate transactions is we are a forking delegate. Let's call it, we manipulate the transaction right before forking. So if we are a forking delegate, or we can bribe a forking delegate, we have the power to manipulate up to 25 transactions, everything around of our own choice, entirely reliable. So we manipulate them, they go into the block, and will be the single source of truth from there. Those three kinds of attacks we have here all manipulate the transaction before it goes into the block. So we call this kind of transactions pre-block, this kind of attacks, pre-block attacks. I hope I can rotate this thing. Oh well, doesn't matter too much. Beautiful. Which brings us to the other side of this line, which is post-block attacks. The advantage of pre-block attacks is that as soon as a manipulated transaction makes it into a block, this manipulation will spread across the whole network, and everybody sees the manipulated transactions. So everybody has the same state of account balances after receiving the block. Post-block attacks work a little bit different. Post-block attacks take a block, manipulate a transaction or multiple transactions within that block without invalidating the signature, so the same way as before, but do that on a block base. So the first case we have here is, I mean, we basically do it the same way as we did here in the middle. We manipulate the block by spawning relay nodes. Spawn relay nodes and manipulate block. Manipulate blocks, which gives us the situation that part of the network will have our manipulated blocks, and part of the network have the original block. Both the original and the manipulated block are valid in terms of the signature. This is because of the collision we saw before. Multiple recipient addresses mapped to the same byte representation. And this gives us different balances for different nodes. Because when a node applies the block, it updates the balances table, and different nodes get different balances. And at the point we have balance changes that affect voting behavior or ranks in the voting list, we get to the situation that multiple nodes have different voting tables. And when the order of the top 101 changes, this nodes get a different expected forking order, which means that one part of the network with the original block expects one forking order, and one part of the other part of the network that gets the manipulated block expects a different forking order, and those groups start to reject the blocks of the other group because they say, okay, this delegate is in position 5 and I expected it to be in position 6, so I'm going to reject the block. But both of these groups will continue to fork with their own expected voting table, which leads to a fork cause 3. Fork cause 3 means that different nodes expect different delegates to fork in a certain block, which is really bad. Nice network split. This can be repeated again and again and again, and brings the whole network into chaos if you want. Next attack is we do not manipulate recipients that have any voting power. So we just change account balances. And what we do is, let's say, manipulate recipient with no voting power. This leads to different account balances. And as an attacker, I now send a send transaction that sends funds from one of the manipulated recipients somewhere, and part of the network will apply the transaction because I have enough funds on that account, and the other part of the network will reject that transaction because they say, okay, this account does not have enough balance to send this transaction, which means we get a nice fork. Don't know if that one has a name. It can be created relatively simple by just manipulating a single block, a single transaction within that block, and just sending a transaction afterwards that uses account balance, which is existing in one part of the network and not existing on the other part of the network. So in this case, the attacker has control over the recipient address because the attacker wants to spend money from there. Manipulate recipients under Okay. Now we have the last attack that I'm going to talk about today, which is a variation of this one we talked about before, but in this case, we don't manipulate recipients of our own, but recipients we know that are going to send monies in the near future. Manipulate recipients, we know that will send money soon. This leads to a network split that triggers as soon as the owner of that recipient address wants to move the funds. And in one part of the network, this send transaction will be valid, and in the other part of the network, this transaction will not be valid. You can do that very nicely with a deposit address of an exchange, and because you know those exchanges will send the money from the deposit address at some time in the near future, you have a nice little time bomb that triggers delayed as soon as the owner of the address moves the funds away. So we have a fork, and additionally we have the potential of delisting the affected coin, Lisk or whatever derivative, because of the potential losing of money for the exchange. So this is it pretty much. These are the attacks I examined. I owe a lot of credit goes to Isabella Dell, who reviewed this bug, prepared the responsible disclosure with me, and helped me to brainstorm about the consequences that this bug has. So thank you very much, Isabella. One of the greatest minds in the industry. Thank you. This is it from my side. I am going to publicly submit a pull request on Wednesday morning. So in 2 days, this pull request will not contain any sign that the changes I do have a security impact. This will be about transaction serialization, very blah blah blah, academic tone in the description, and but it will be public on Wednesday morning. Until then, you all get access to the patch. I am there today and tomorrow for any kind of questions. And yeah, I hope we all work together hand in hand to get this thing fixed in order to avoid chaos for the entire industry. I'm here for any kind of questions now within this meeting. I have all the chats available on my other screen, so feel free to raise questions that I am going to repeat for the others, or just write them in the chat of this Zoom meeting.
Thank you very much, Simon. The bug looks very, very severe indeed. The question from my side is like, basically, thank you very much for dealing with the stuff in the way you did. And also because of the severity of the bug, I would feel much more comfortable if we collaborate on your patch release and make the fix under your name, of course, but let's just do it much faster, possibly even today. Is it also okay for you?
That depends on the okay from the other projects. I'm perfectly fine submitting it today, getting it deployed today, but I don't want to have a patch in one project that is like a receipt for an attack for the other project. We get okay from Rise in the chat, which is cool.
Okay, so the question are the projects then?
Yeah, but I think this is something we can discuss afterwards if we get if everybody is in the industry is comfortable with doing it sooner than Wednesday. I'm perfectly fine with that. So I think we should discuss that in private.
Sure. Okay. Thank you so much, Simon.
Sure.
Well, okay. Okay, I will have a look in details on your pull request, but for now, like, looks very good so far as I've seen. Thank you for like covering the case with 0L address as well. Let's have a look on it with a call I on it. Thank you so much.
Yeah, you're welcome. The pull request is in a private repository right now. You can send me all your SSH keys, and you will get access to that pull request for further review and yeah, discussion about that.
Take care of that. The pull request is under your name for sure. Thank you so much.
Yeah, thank you. Okay. Yeah. Are there any other questions I can answer now? We want to set up a chat where we can all coordinate afterwards, which is great. Is there something that I can demonstrate now? If not, I'm going to close this meeting. I thank you very much for your time and the patience. I know I planned that a long time beforehand, but as you can see, this is something you don't mess around with. So yeah.
Yeah. Thank you so much. No more questions from thank you.
All right, thank you very much. I'm closing this meeting. It was a pleasure, and I will follow up in that chat. Bye-bye.